Ancient Greek storytellers could never have imagined when they first whispered tales of a beautiful huntress named Callisto, transformed by jealous gods into a bear and cast among the stars. This distant moon, bearing her name across the millennia, has become one of the most intriguing destinations in our cosmic neighbourhood, a place where ancient craters tell stories spanning 4 billion years, where ice and rock mingle in ways that puzzle scientists to this day, and where a hidden ocean may lie waiting beneath a surface that has remained virtually unchanged since the earliest days of our solar system. The story of Callisto begins not in the frigid reaches of space where this moon silently orbits the giant planet Jupiter, but rather in the warm Italian nights of early 1610, when a curious mathematician and astronomer named Galileo Galilei turned a newly improved instrument toward the heavens and changed our understanding of the universe forever. Galileo had heard reports of a Dutch invention, a tube fitted with carefully ground lenses that could make distant objects appear closer, and with characteristic ingenuity he set about constructing his own version, each iteration more powerful than the last. By January of that transformative year, Galileo possessed a telescope capable of magnifying objects roughly 20 times. A modest power by modern standards, but revolutionary for its era, and he aimed this precious instrument at the brilliant wandering star the ancients had named after the king of their gods. What Galileo observed on those cold January nights would shake the foundations of astronomy and philosophy alike. Near the bright disk of Jupiter, he noticed what he initially took to be small fixed stars, 3 tiny points of light arranged in a line with the planet. Yet as he continued his observations over subsequent nights, Galileo realized with growing excitement that these were not fixed stars at all. They moved, changing their positions relative to Jupiter in ways that could only mean one thing. These small bodies were orbiting the giant planet, just as our own moon orbits Earth. Within weeks, Galileo had identified 4 distinct satellites circling Jupiter, and among them was the outermost member of this celestial family, the world we now call Callisto. The significance of this discovery extended far beyond the mere addition of 4 new objects to astronomical catalogues. In an age when the prevailing cosmology, championed by the Catholic Church and rooted in the ancient teachings of Aristotle and Ptolemy, placed Earth firmly at the centre of all creation, Galileo's moons presented a profound challenge. Here was undeniable proof that not everything in the heavens revolved around our planet. Jupiter possessed its own system of satellites, a miniature solar system in its own right, and this observation lent powerful support to the controversial heliocentric model proposed by Nicholas Copernicus decades earlier. The 4 moons became known collectively as the Galilean satellites, a tribute to their discoverer that persists to this day. Galileo himself did not name the individual moons. He referred to them simply by numbers, designating them 1 through 4 based on their distance from Jupiter, with Callisto being the 4th and most distant of the quartet. The names we use today came from a German astronomer named Simon Marius, who claimed to have observed the moons independently around the same time as Galileo, though his claim has been disputed by historians. Marius suggested naming the satellites after lovers of Zeus, the Greek equivalent of Jupiter, and so the outermost moon received the name Callisto, after a huntress whose tragic story had been told and retold throughout the ancient Mediterranean world. The mythological Callisto was said to be a nymph devoted to the goddess Artemis, sworn to a life of chastity and dedicated to the hunt. Her beauty, however, caught the attention of Zeus, the king of the Olympian gods, who was notorious for his romantic pursuits despite his marriage to the goddess Hera. According to the most common version of the myth, Zeus disguised himself as Artemis to approach Callisto and seduce her, a deception that resulted in Callisto becoming pregnant. When her condition became apparent, Artemis banished her from the company of hunters for breaking her vow of chastity, and Callisto gave birth to a son named Arcas. The jealous Hera, learning of yet another of her husband's infidelities, transformed the unfortunate Callisto into a bear, condemning her to wander the forests in animal form. Years later, when Arcas had grown into a young hunter, he encountered a bear in the woods, not knowing it was his transformed mother. Just as Arcas was about to kill the bear with his spear, Zeus intervened, transforming both mother and son into constellations and placing them in the sky as Ursa Major and Ursa Minor, the Great Bear and the Little Bear. In some versions of the tale, Hera's anger was not satisfied even by this celestial exile, and she convinced the sea god Poseidon to forbid the bear constellations from ever dipping below the horizon to bathe in the ocean, which is why these northern constellations appear to circle endlessly around the celestial pole, never setting for observers at northern latitudes. This story of transformation, exile, and eternal wandering seems strangely fitting for the moon that bears Callisto's name. Like its mythological namesake, the moon Callisto exists in a kind of cosmic isolation, orbiting far from its parent planet in a realm of perpetual cold and darkness, its ancient surface bearing the scars of countless impacts accumulated over billions of years. The connection between myth and moon adds a layer of poetry to our scientific exploration, reminding us that humanity has always sought to find meaning and narrative in the lights that dot our night sky. Following Galileo's initial discovery, astronomers throughout the 17th, 18th, and 19th centuries continued to observe Callisto and its sibling moons, gradually accumulating knowledge about their orbital periods, their brightness variations, and their positions relative to Jupiter. These observations serve practical purposes as well as scientific ones. The regular, predictable motions of the Galilean moons provided a natural clock visible from anywhere on Earth, and navigators soon realized that by carefully timing the eclipses of these moons as they passed behind Jupiter, they could determine their longitude at sea, a problem that had bedeviled sailors for centuries. The moons of Jupiter thus played a role in the great age of exploration, helping ships find their way across trackless oceans. Yet for all the observations made through ever-improving telescopes, Callisto remained little more than a point of light for over 3.5 centuries after its discovery. Astronomers could measure its orbit with exquisite precision, calculate its mass from its gravitational effects, and even make rough estimates of its size, but the actual nature of this distant world remained shrouded in mystery. What did its surface look like? What was it made of? Did it possess an atmosphere? These questions would have to wait for the space age to provide answers, for only by sending robotic emissaries across the vast gulf between Earth and Jupiter could humanity hope to truly see and understand the outermost Galilean moon. The first spacecraft to venture into the realm of Jupiter were the twin Pioneer probes, numbered 10 and 11, launched in 1972 and 1973 respectively. These hardy machines were designed primarily to test whether spacecraft could survive passage through the asteroid belt and navigate the intense radiation environment surrounding Jupiter, and they carried relatively simple instruments compared to later missions. Pioneer 10 made its closest approach to Jupiter in December of 1973, passing within about 130,000 kilometers of the planet's cloud tops and returning the first close-up images of the giant world. Pioneer 11 followed a year later, using Jupiter's gravity to redirect its trajectory towards Saturn. The Pioneer spacecraft provided humanity's first fleeting glimpses of the Galilean moons from relatively close range. But their cameras were not designed for detailed imaging of these small worlds, and the images they returned showed Callisto and its siblings as little more than fuzzy disks with hints of surface markings. Nevertheless, these pioneering missions proved that the journey to Jupiter was possible and paved the way for far more ambitious explorations to come. The Voyager program represented a quantum leap in our ability to explore the outer solar system. Voyager 1 and Voyager 2 launched within weeks of each other in the summer of 1977, carried sophisticated imaging systems, spectrometers, and other instruments capable of revealing the Galilean moons in unprecedented detail. Voyager 1 reached Jupiter in March of 1979, followed by Voyager 2 in July of that same year, and together these spacecraft transformed our understanding of the Jovian system. When the Voyager cameras turned toward Callisto, they revealed a world unlike anything astronomers had expected. The moon's surface was absolutely saturated with impact craters, more heavily cratered than any other body yet observed in the solar system. Crater upon crater upon crater covered every visible portion of the surface. The scars of billions of years of cosmic bombardment preserved in pristine detail. Unlike the other Galilean moons, which showed evidence of geological activity that had resurfaced portions of their exteriors, Callisto appeared to be a world frozen in time, its surface essentially unchanged since the early days of the solar system, when impacts were far more frequent than they are today. The Voyager images also revealed enormous multi-ring impact structures, the largest of which was named Valhalla, after the Great Hall of Slain Warriors in Norse mythology. Valhalla dominates one hemisphere of Callisto, its central bright region spanning roughly 360 kilometers in diameter, surrounded by concentric rings of ridges and troughs that extend outward for nearly 2,000 kilometers from the center. This structure records an ancient catastrophic impact, a collision so powerful that it sent shockwaves rippling through Callisto's icy crust, creating the distinctive ring pattern visible today. The presence of such well-preserved impact structures confirm that Callisto's surface is extremely old, a relic of the solar system's violent youth. Voyager's instruments also detected that Callisto's surface is composed primarily of water ice mixed with darker rocky material, giving the moon its characteristic brownish-grey coloration. The ice is not pure and white like freshly fallen snow on Earth, but rather dirty and ancient, contaminated by billions of years of accumulated dust and radiation-processed organic compounds. This mixture of ice and rock would prove to be a defining characteristic of Callisto, distinguishing it from its more geologically active siblings and providing clues about how the moon formed and evolved over time. To truly understand Callisto's place in the cosmic order, we must consider it within the context of its remarkable family, the 4 Galilean moons that together form a system of worlds as diverse and fascinating as any collection of planets. These 4 satellites, in order of their distance from Jupiter, are Io, Europa, Ganymede, and Callisto, and each possesses a distinct character shaped by its unique position and history. Io, the innermost of the Galilean moons, orbits Jupiter at an average distance of approximately 422,000 kilometers, completing one orbit every 1.77 Earth days. This proximity to the giant planet subjects Io to tremendous tidal forces, the gravitational pull of Jupiter literally flexing and squeezing the moon's interior, generating enormous amounts of heat through friction. This tidal heating has made Io the most volcanically active body in the solar system, its surface constantly being reshaped by eruptions that spew sulfurous compounds across the landscape, painting the moon in vivid yellows, oranges and reds. Io is a world of fire and brimstone, as alien and hostile as any place imaginable. Europa, the second Galilean moon, orbits at about 671,000 kilometers from Jupiter with a period of 3.55 days. Slightly smaller than Earth's moon, Europa presents a surface of water ice, crisscrossed by countless reddish-brown streaks and cracks, with remarkably few impact craters visible. This relative absence of craters indicates that Europa's surface is geologically young, constantly being renewed by processes that erase the scars of ancient impacts. Scientists believe that beneath Europa's icy shell lies a global ocean of liquid water, kept warm by tidal heating similar to, but less intense than that affecting Io. This subsurface ocean has made Europa one of the most compelling targets in the search for extraterrestrial life, a place where conditions might be suitable for organisms to thrive in the darkness beneath the ice. Ganymede, the third moon outward, holds the distinction of being the largest moon in the entire solar system, exceeding even the planet Mercury in diameter, though not in mass. Orbiting at roughly 1,070,000 kilometers from Jupiter with a period of 7.15 days, Ganymede displays a surface divided into two distinct terrain types: ancient, heavily cratered dark regions and younger, lighter regions marked by grooves and ridges that suggest past geological activity. Ganymede is the only moon known to generate its own magnetic field, evidence of a liquid iron core deep within its interior, and like Europa, it may harbour a subsurface ocean beneath its icy crust. And then there is Callisto, the outermost and in many ways the most enigmatic of the Galilean siblings. Callisto orbits Jupiter at an average distance of approximately 1,883,000 kilometers, nearly twice as far from the planet as Ganymede and more than 4 times the distance of Io. At this remote location, Callisto takes 16.69 Earth days to complete a single orbit, the longest orbital period of any Galilean moon. This great distance from Jupiter has profound implications for Callisto's nature and evolution. The orbital arrangement of the inner 3 Galilean moons exhibits a beautiful mathematical relationship known as the Laplace resonance. For every orbit Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This 1:2:4 ratio is maintained by gravitational interactions between the moons, their mutual tugging keeping them locked in this precise orbital dance. The resonance has important consequences for the moon's internal heating, as the gravitational interactions prevent their orbits from becoming perfectly circular, maintaining the slight eccentricities that drive tidal flexing and generate internal heat. Callisto, however, stands apart from this resonance. Its orbit is not locked into any simple ratio with its siblings, and its great distance from Jupiter means that tidal forces acting upon it are far weaker than those affecting the inner moons. This orbital isolation has allowed Callisto to evolve along a fundamentally different path than Io, Europa, and Ganymede. Without significant tidal heating to drive geological activity, Callisto has remained cold and quiescent, its interior never warming enough to fully differentiate into distinct layers of rock and metal, its surface never being renewed by volcanism or tectonics. Callisto is, in essence, a frozen relic, a world that has changed little since its formation over 4 billion years ago. Like all the Galilean moons, Callisto is tidally locked to Jupiter, meaning that the same hemisphere always faces the planet, just as the same side of Earth's moon always faces our world. This synchronous rotation results from the gradual slowing of a moon's spin by tidal forces over millions of years, until the rotation period matches the orbital period exactly. For Callisto, this means that one complete day from noon to noon takes the same 16.69 Earth days as one complete orbit. Observers standing on Callisto's Jupiter-facing hemisphere would see the giant planet hanging motionless in their sky, its bands and storms slowly rotating, but the planet itself never rising or setting. Those on the opposite hemisphere would never see Jupiter at all, their sky dominated instead by the distant sun and the countless stars. The view from Callisto's surface would be unlike anything experienced on Earth. Jupiter would appear enormous in the sky of the near hemisphere, spanning roughly 8 degrees of arc, about 16 times the apparent size of our moon as seen from Earth. The planet's colourful bands, its swirling storms including the famous Great Red Spot, and the constant dance of its other moons would provide an ever-changing spectacle. Yet despite its visual dominance, Jupiter would provide little warmth to Callisto's frozen surface. The Sun, reduced by distance to a brilliant but small point of light, delivers only about 1/25 the solar energy that reaches Earth, leaving Callisto perpetually cold, with surface temperatures averaging around -139 degrees Celsius, or roughly -218 degrees Fahrenheit. Callisto ranks as the third largest moon in our solar system, surpassed only by Ganymede and Saturn's giant moon Titan. With a diameter of 4,821 kilometers, Callisto is nearly as large as the planet Mercury, which measures 4,879 kilometers across. If Callisto orbited the Sun independently rather than circling Jupiter, it would easily qualify as a planet in its own right, a world of substantial size and complexity. The Moon's radius of approximately 2,410 kilometers means that its circumference stretches over 15,100 kilometers, a vast expanse of ancient, cratered terrain. To put Callisto's size in perspective, consider that Earth's moon has a diameter of only 3,474 kilometers, making Callisto nearly 40% larger than our own familiar satellite. Mars, the fourth planet from the Sun, measures 6,792 kilometers in diameter, so Callisto reaches about 71% of the red planet's size. This makes Callisto a truly substantial world, large enough to have significant gravity, to potentially retain a thin atmosphere, and to harbour complex internal structures. The mass of Callisto amounts to approximately 1.08 times 10 to the 23rd kilograms, which translates to roughly 1.8% of Earth's mass, or about 1.4 times the mass of our Moon. This mass, combined with Callisto's size, yields a bulk density of only 1.83 grams per cubic centimetre, one of the lowest densities of any major moon in the solar system. For comparison, Earth's average density is 5.51 grams per cubic centimetre, while even our relatively lightweight moon comes in at 3.34 grams per cubic centimetre. This remarkably low density tells us something fundamental about Callisto's composition. Pure water ice has a density of about 0.92 grams per cubic centimetre, while typical silicate rocks range from 2.5 to 3 grams per cubic centimetre, and iron averages around 7.8 grams per cubic centimetre. Callisto's density of 1.83 grams per cubic centimetre indicates that the Moon must be composed of a roughly equal mixture of ice and rock by mass, with no significant concentration of dense metallic materials, like the iron cores found in terrestrial planets. This ice-rock mixture permeates Callisto's entire structure, from surface to centre, in a way that distinguishes it from most other large bodies in the solar system. Standing on the surface of Callisto, you would experience a gravitational pull of approximately 1.24 meters per second squared, or about 12.6% of Earth's surface gravity. A person weighing 100 kilograms on Earth would weigh only 12.6 kilograms on Callisto, light enough to leap several meters into the thin air with minimal effort. This weak gravity has important implications for Callisto's ability to retain an atmosphere, for the trajectories of objects thrown or launched from its surface, and for any future human activities that might take place on this distant world. The escape velocity from Callisto's surface is approximately 2.44 kilometers per second, compared to 11.2 kilometers per second for Earth. This relatively low escape velocity means that gases have an easier time escaping from Callisto into space, which partly explains why the Moon possesses only the thinnest wisp of an atmosphere, despite its substantial size. It also means that spacecraft landing on or departing from Callisto would require far less fuel than similar operations on Earth, a consideration that has made Callisto an attractive destination for proposed future human missions. Callisto's surface presents one of the most extraordinary landscapes in the solar system, a terrain so thoroughly marked by impacts that it serves as a kind of cosmic record book, documenting billions of years of bombardment by asteroids, comets, and other debris. When scientists describe Callisto as the most heavily cratered body in the solar system, they are not engaging in hyperbole. Every square kilometre of Callisto's surface bears the scars of ancient collisions, craters overlapping craters in a complex palimpsest of destruction and preservation. The reason for this extreme cratering lies in Callisto's geological inactivity. On worlds with active geology, like Earth or Io, surface features are constantly being erased and renewed. Volcanic eruptions bury old craters under fresh lava. Tectonic forces crack and shift the crust. Erosion by wind and water wears down elevated features, and the passage of time gradually erases the evidence of past impacts. But Callisto has experienced none of these rejuvenating processes for billions of years. Without volcanism, without tectonics, without significant erosion, the craters that formed during the solar system's youth have remained essentially unchanged, accumulating one atop another until the surface reached a state of saturation equilibrium, where new craters can only form by destroying older ones. The age of Callisto's surface has been estimated at approximately 4 billion years, dating back to a period known as the Late Heavy Bombardment, when the inner solar system was subjected to an intense rain of impacts from debris left over from planetary formation. This bombardment scarred the surfaces of the Moon, Mercury, Mars, and many other bodies, but most of these worlds have experienced subsequent geological activity that has partially or completely erased the evidence. Callisto alone preserves a nearly complete record of this violent epoch, making it an invaluable laboratory for understanding the early history of our solar system. The most spectacular feature on Callisto's surface is the Valhalla impact basin, a structure so large that it dominates an entire hemisphere of the Moon. Valhalla's central region appears as a bright, relatively smooth plain, approximately 360 kilometers in diameter, the frozen remnant of the impact that created it. Surrounding this central zone are concentric rings of ridges and troughs that extend outward like ripples frozen in stone, reaching distances of up to 1,900 kilometers from the center. The outermost rings are spaced roughly 50 to 100 kilometers apart, creating a pattern that resembles the growth rings of an ancient tree. The formation of Valhalla's distinctive multi-ring structure can be understood by considering the nature of Callisto's crust at the time of impact. Unlike the rigid, rocky crust of a body like the Moon, Callisto's outer layers consist of ice mixed with rock, a material that behaves somewhat like a very viscous fluid over long timescales. When a large impactor struck Callisto billions of years ago, it excavated a tremendous crater and sent shockwaves rippling through the icy crust. These shockwaves caused the ice to flow and deform, creating the concentric ridges as the disturbed material settled into its final configuration. The bright central region may represent material that welled up from below to fill the initial crater cavity, or it may be composed of relatively clean ice excavated from depth by the impact. The second largest multi-ring structure on Callisto is the Asgard basin, named after the home of the gods in Norse mythology, continuing the naming theme established by Valhalla. Asgard measures approximately 1,600 kilometers in diameter and displays a similar pattern of concentric rings, though it is somewhat smaller and less well preserved than Valhalla. Together, Valhalla and Asgard represent the two largest impact structures on Callisto and among the largest in the entire solar system. Monuments to catastrophic collisions that occurred when the solar system was young. Beyond these giant basins, Callisto's surface is peppered with craters of every size, from vast structures hundreds of kilometers across down to tiny pits, only meters in diameter. Some of the larger named craters include Adlinda, Heimdall, Skuld, and Loffen, their names drawn from various mythological traditions. Each crater tells a story of a moment frozen in time, an instant when a chunk of cosmic debris travelling at tremendous speed slammed into Callisto's icy surface, excavating material, melting ice, and leaving a permanent scar on the landscape. One of the most intriguing aspects of Callisto's craters is their relatively subdued appearance compared to craters on rocky bodies like the Moon or Mercury. Fresh lunar craters typically display sharp, well-defined rims, steep walls, and prominent central peaks, features that can persist for billions of years in the airless lunar environment. Callisto's craters, by contrast, tend to have softer, more rounded profiles with shallower depths and less pronounced rims. This difference reflects the behaviour of ice under Callisto's conditions. Over extremely long timescales, ice behaves as a viscous material, slowly flowing under the influence of gravity in a process called viscous relaxation. On Callisto, this process has gradually softened the sharp features of ancient craters, causing crater walls to slump, floors to rise, and rims to spread. The rate of viscous relaxation depends on temperature, with warmer ice flowing more readily than colder ice, so the degree of crater degradation provides information about Callisto's thermal history. The fact that even ancient craters remain recognizable indicates that Callisto's surface has been extremely cold for most of its history, cold enough to preserve crater forms that would have long since disappeared on a warmer world. The surface composition of Callisto has been studied through spectroscopic observations from Earth and from spacecraft, revealing a complex mixture of materials. Water ice dominates the composition, but it is not the pure white ice of a terrestrial glacier. Instead, Callisto's surface ice is intimately mixed with dark, rocky material that gives the Moon its characteristic brownish-grey colour, making it one of the darkest of the Galilean moons, despite its icy composition. The exact nature of this dark material remains somewhat uncertain, but it likely includes silicate minerals, carbon-rich organic compounds, and possibly iron-bearing materials. The mixing of ice and dark material on Callisto's surface may result from several processes operating over billions of years. Micrometeorite bombardment continuously churns the uppermost layers of the surface, mixing materials and exposing fresh ice to space. Radiation from the Sun and from Jupiter's magnetosphere chemically alters surface materials, breaking down simple molecules and creating more complex organic compounds. Sublimation of ice, the direct transition from solid to gas that occurs even at Callisto's frigid temperatures, may concentrate dark, non-volatile materials on the surface as ice is lost to space. The result is a surface layer of dirty processed ice that tells a complex story of exposure and alteration over geological time. Beneath this battered ancient surface lies an interior that has puzzled scientists since the first detailed observations were made. Unlike most large moons and planets, which have differentiated into distinct layers of different compositions, Callisto appears to have only partially differentiated, retaining a relatively homogeneous mixture of ice and rock throughout much of its interior. This partial differentiation represents one of the most intriguing mysteries of Callisto's nature. To understand why this is surprising, consider how differentiation typically occurs. When a large body forms from the accumulation of smaller pieces, the heat generated by impacts and by the decay of radioactive elements within the body causes the interior to warm. If the temperature rises high enough, the material becomes soft or even molten, allowing denser components like iron and rock to sink toward the center, while lighter materials like ice rise toward the surface. This process, called differentiation, produces a layered structure with a dense core, a rocky mantle, and an icy outer shell, the configuration seen in many large moons and planets. Ganymede, Callisto's larger sibling, has clearly undergone extensive differentiation. Observations indicate that Ganymede possesses a metallic iron core, a rocky mantle, and an outer layer of ice, a structure that reflects thorough separation of materials by density. Europa, too, shows evidence of differentiation, with a metallic core, rocky interior, and icy shell. Even Io, despite its ongoing volcanic activity constantly reworking its interior, has differentiated into a metallic core surrounded by a rocky mantle and crust. Callisto, however, tells a different story. Measurements of the moon's gravitational field, made by tracking the motion of spacecraft flying past, indicate that Callisto's interior does not have the strongly layered structure expected of a fully differentiated body. Instead, the density increases only gradually from surface to center, suggesting that ice and rock remain mixed throughout much of the interior rather than having separated into distinct layers. Some differentiation has occurred, as evidenced by the density gradient, but the process appears to have been incomplete. Several hypotheses have been proposed to explain Callisto's partial differentiation. One possibility is that Callisto simply never got hot enough to allow complete separation of materials. The moon's great distance from Jupiter means it experiences minimal tidal heating, unlike its inner siblings, and if Callisto formed slowly from cold materials, it might never have accumulated enough heat to fully melt its interior. Another possibility involves the presence of substances that inhibit differentiation, such as ammonia mixed with the water ice, which could lower melting temperatures and alter the rheological properties of the interior in ways that prevent efficient separation. Recent models suggest that Callisto may have experienced a period of partial melting early in its history, allowing some differentiation to occur, but that this process was arrested before completion. The heat from radioactive decay and from accretional impacts may have been sufficient to warm the interior and initiate differentiation, but as heat was lost to space and radioactive elements decayed, the interior cooled and solidified before the separation of ice and rock could be completed. The result is the partially differentiated state observed today, a frozen snapshot of an incomplete geological process. Despite this incomplete differentiation, there is compelling evidence that Callisto may harbour a layer of liquid water somewhere within its interior, a subsurface ocean hidden beneath the icy crust. This evidence comes primarily from measurements made by the Galileo spacecraft, which orbited Jupiter from 1995 to 2003 and made multiple close flybys of all 4 Galilean moons. During its encounters with Callisto, Galileo detected perturbations in Jupiter's magnetic field near the Moon that are best explained by the presence of an electrically conducting layer within Callisto's interior. Jupiter's powerful magnetic field sweeps past Callisto as the planet rotates, and if there is a conducting layer within the Moon, it will generate induced currents that create a secondary magnetic field opposing the external field. The pattern of magnetic variations detected by Galileo matches what would be expected from a subsurface ocean of salty water, which would be an excellent electrical conductor. If this interpretation is correct, Callisto joins Europa and Ganymede as members of an exclusive club of ocean worlds, moons that harbour vast reservoirs of liquid water beneath their frozen surfaces. The implications of this discovery extend far beyond mere geological curiosity, touching on some of the most profound questions humanity has ever asked about the nature of life and its distribution throughout the cosmos. Chapter 8: Callisto's Subsurface Ocean, a hidden world of liquid water. The possibility that Callisto conceals an ocean beneath its ancient, cratered surface represents one of the most exciting discoveries in planetary science, transforming our understanding of this seemingly dead world into something far more dynamic and potentially significant. While Europa has long captured the imagination as the most promising ocean world in the outer solar system, the evidence for liquid water within Callisto suggests that subsurface oceans may be far more common than scientists once believed, hidden beneath the icy shells of countless moons and dwarf planets throughout our cosmic neighbourhood. The evidence for Callisto's ocean comes primarily from the Galileo spacecraft's magnetometer, an instrument designed to measure the strength and direction of magnetic fields with exquisite precision. As Galileo flew past Callisto on multiple occasions between 1996 and 2001, this instrument detected subtle but unmistakable variations in the magnetic environment near the Moon. These variations could not be explained by a permanent internal magnetic field like that possessed by Ganymede or Earth, but instead showed a pattern consistent with an induced magnetic field, one generated in response to the changing external magnetic field of Jupiter. The physics behind this induced field is elegantly simple. Jupiter possesses the most powerful magnetic field of any planet in our solar system, generated by currents flowing within the planet's metallic hydrogen interior. This magnetic field rotates with Jupiter, completing one rotation approximately every 10 hours, and as it sweeps past the orbiting moons, it creates a constantly changing magnetic environment. If a moon contains a layer of electrically conducting material, this changing external field will induce electrical currents within that layer, and these currents will in turn generate their own magnetic field that partially opposes the external field. By measuring the characteristics of this induced field, scientists can infer the properties of the conducting layer that produced it. For Callisto, the induced magnetic field measurements suggest the presence of a conducting layer at a depth of perhaps 150 to 250 kilometers below the surface. The most plausible candidate for this conducting layer is liquid water containing dissolved salts, which would make it an excellent electrical conductor. Pure water ice, by contrast, is a very poor conductor, and the rocky materials within Callisto would not produce the observed magnetic signature. The conclusion seems inescapable. Somewhere within Callisto's icy interior lies a global ocean of salty water, hidden from view but detectable through its electromagnetic fingerprint. Estimating the properties of this putative ocean requires combining the magnetic field measurements with models of Callisto's interior structure and thermal evolution. Current estimates suggest that the ocean may be located at depths ranging from 100 to 200 kilometers below the surface, sandwiched between an outer shell of solid ice and an interior composed of mixed ice and rock. The ocean itself might be anywhere from 10 to several hundred kilometers thick, containing a volume of liquid water that could exceed all the liquid water on Earth's surface. The temperature of this ocean would be determined by the balance between heat flowing outward from Callisto's interior and heat being lost to the cold surface above. Even without significant tidal heating, the decay of radioactive elements within Callisto's rocky component would generate some internal heat, enough perhaps to maintain a layer of liquid water at depth where pressures are high and the melting point of ice is correspondingly lower. The presence of dissolved salts or other antifreeze compounds, like ammonia, could further lower the freezing point, allowing liquid water to persist at temperatures well below 0 degrees Celsius. The composition of Callisto's ocean remains highly uncertain, as no direct measurements have been made. By analogy with other icy bodies and with laboratory experiments on ice-rock mixtures, scientists speculate that the ocean likely contains dissolved salts, including sodium chloride, magnesium sulfate, and possibly other compounds. The concentration of these salts would affect both the ocean's electrical conductivity and its potential as a habitat for life. A very salty ocean, like the Dead Sea on Earth, would be a harsh environment for most organisms, while a less saline ocean might be more hospitable. The discovery of a potential ocean within Callisto raises inevitable questions about the possibility of life in this hidden realm. On Earth, liquid water is considered essential for life, as we know it. And everywhere we find liquid water on our planet, we find life thriving, from the deepest ocean trenches to hot springs and subglacial lakes. The presence of liquid water within Callisto means that at least one of the basic requirements for life is satisfied. But water alone is not sufficient. Life also requires energy sources and chemical building blocks, and whether these are available within Callisto's ocean remains unknown. Compared to Europa, which has become the poster child for ocean world astrobiology, Callisto's ocean presents both advantages and challenges as a potential habitat. Europa's ocean is thought to be in direct contact with a rocky seafloor, where hydrothermal vents might provide the chemical energy and nutrients necessary to support life, similar to the deep-sea vent ecosystems found on Earth. Callisto's ocean, by contrast, may be sandwiched between layers of ice, isolated from any rocky material that might provide chemical sustenance. This configuration would make it more difficult for life to obtain the energy and nutrients it needs, though not necessarily impossible. Some scientists have speculated that Callisto's ocean might still support life if organic compounds and other nutrients were delivered to the Moon during its formation or by subsequent impacts, and if these materials found their way into the ocean over time. Others have suggested that chemical reactions within the ice shell itself might provide some energy for metabolism, or that radioactive decay within the ocean layer could drive chemical reactions that support simple organisms. These ideas remain highly speculative, and the question of whether life could exist within Callisto will likely remain unanswered until future missions can probe the Moon's interior directly. The comparison between Callisto's ocean and those of Europa and Enceladus highlights the diversity of ocean worlds in our solar system. Europa's ocean is estimated to be roughly 100 kilometers deep, lying beneath an ice shell perhaps 15 to 25 kilometers thick, and is probably in contact with a silicate seafloor, where water-rock interactions could provide chemical energy for life. Enceladus, the small moon of Saturn, famous for its spectacular water geysers, has a global ocean beneath an ice shell that is thinnest at the South Pole, where the geysers erupt. The Cassini spacecraft detected hydrogen gas in Enceladus's plumes, suggesting active hydrothermal processes on the ocean floor. Callisto's ocean, if it exists, would be different from both of these. Located deeper beneath a thicker ice shell, potentially isolated from rocky material, and lacking the dramatic surface expressions seen at Europa and Enceladus, Callisto's ocean would be a more hidden and perhaps more quiescent environment. Yet its very existence expands our understanding of where liquid water can persist in the solar system, suggesting that oceans may be common features of large icy bodies throughout the outer reaches of planetary systems. The implications of widespread subsurface oceans extend beyond our own solar system to the countless exoplanets and exomoons orbiting other stars. If moons like Callisto can maintain liquid water oceans for billions of years despite their great distance from the Sun and their lack of significant internal heating, then similar ocean worlds might be common throughout the galaxy. The search for life beyond Earth thus expands from the traditional focus on planets in the habitable zone, where surface liquid water is possible, to include the hidden oceans of icy moons far from their parent stars. Chapter 9. The Thin Atmosphere of Callisto. Whispers of gas in the void. Surrounding Callisto's ancient surface is the thinnest wisp of an atmosphere, so tenuous that it barely deserves the name, yet significant enough to provide important clues about the processes occurring on and within this distant moon. This atmosphere, more properly called an exosphere because it's so thin that individual gas molecules rarely collide with one another, was first detected by the Galileo spacecraft and has since been studied through Earth-based observations and theoretical modelling. The primary component of Callisto's atmosphere is carbon dioxide, detected by Galileo's near-infrared mapping spectrometer during close flybys of the Moon. The surface pressure of this carbon dioxide atmosphere is estimated at approximately 7.5 trillionths of a bar, or about 75 trillionths of Earth's atmospheric pressure at sea level. To put this in perspective, the best laboratory vacuums on Earth typically achieve pressures millions of times higher than Callisto's atmospheric pressure. This is an atmosphere in name only, a collection of scattered molecules with so much space between them that they behave more like independent particles than a continuous fluid. The source of Callisto's carbon dioxide atmosphere is thought to be the sublimation of carbon dioxide ice from the Moon's surface. Despite the extremely cold temperatures, some carbon dioxide molecules have enough thermal energy to escape from the surface ice into the surrounding space, creating a tenuous envelope of gas around the Moon. This process is enhanced on the sunlit hemisphere, where temperatures are slightly higher and reduced on the night side and in permanently shadowed regions. The result is an atmosphere that varies in density depending on location and time, thickest where the sun shines most directly and thinnest in the cold shadows of crater walls. In addition to carbon dioxide, there is evidence for molecular oxygen in Callisto's exosphere, though in even smaller quantities. This oxygen is not produced by biological processes as on Earth, but rather by the radiolysis of water ice, the breaking apart of water molecules by energetic radiation from the Sun and from Jupiter's magnetosphere. When high-energy particles strike water ice, they can split the water molecules into hydrogen and oxygen. The lightweight hydrogen atoms escape easily into space, while the heavier oxygen atoms and molecules may linger near the surface, contributing to the exosphere. The detection of oxygen in Callisto's atmosphere was made through observations of oxygen emissions in the ultraviolet portion of the spectrum, using the Hubble Space Telescope and other instruments. These emissions occur when oxygen atoms are excited by solar radiation and then release energy as they return to their ground state. The intensity of these emissions provides information about the abundance and distribution of oxygen in the exosphere, though significant uncertainties remain. The processes that create and destroy Callisto's atmosphere operate in a delicate balance. On the creation side, sublimation releases carbon dioxide and other volatile compounds from the surface ice, while radiolysis produces oxygen from water ice. On the destruction side, the solar wind and Jupiter's magnetospheric particles continuously strip atoms and molecules from the exosphere, carrying them away into space. The weak gravity of Callisto, with its escape velocity of only 2.44 kilometers per second, makes it relatively easy for gas molecules to escape, especially the lighter species like hydrogen. The balance between these processes determines the steady-state density of Callisto's atmosphere, which appears to have remained relatively constant over the timescales of human observation. However, over geological time, the continuous loss of atmospheric gases must be balanced by continuous replenishment from the surface, or the atmosphere would eventually disappear entirely. The fact that Callisto retains even this thin exosphere after billions of years suggests that the surface ice continues to release volatile compounds, maintaining the atmospheric envelope against ongoing losses. Comparing Callisto's atmosphere to those of other moons provides interesting insights into the factors that determine atmospheric properties. Titan, Saturn's largest moon, possesses a thick nitrogen atmosphere with a surface pressure about 1.5 times that of Earth, dense enough to obscure the surface from view and to support complex atmospheric chemistry. Triton, Neptune's largest moon, has a thin nitrogen atmosphere with a surface pressure of about 14 microbars, much thicker than Callisto's, but still extremely tenuous by terrestrial standards. Io's atmosphere, composed primarily of sulfur dioxide from volcanic emissions, varies dramatically in density depending on volcanic activity and the Moon's position relative to Jupiter. Europa and Ganymede, Callisto's Galilean siblings, also possess thin oxygen exospheres produced by radiolysis of their surface ice, similar to the process operating on Callisto. The density of these exospheres varies among the moons, influenced by factors including surface temperature, radiation environment, and the presence of other atmospheric species. Callisto's exosphere appears to be among the thinnest of the Galilean moons, consistent with its greater distance from Jupiter and correspondingly lower radiation flux. The study of Callisto's atmosphere, thin as it is, provides valuable information about surface processes and the interaction between the Moon and its space environment. The composition of the exosphere reflects the composition of the surface ice, while the density and distribution of atmospheric gases reveal information about sublimation rates, radiation effects, and atmospheric escape processes. Future missions, equipped with more sensitive instruments, may be able to detect additional atmospheric species and map their distribution across the Moon's surface, providing new insights into Callisto's complex environmental processes. Chapter 10: Space Exploration of Callisto, Robotic Emissaries to a Distant World. The story of humanity's exploration of Callisto is a tale of remarkable engineering achievements, of spacecraft travelling billions of kilometres through the hostile environment of space to return images and data from a world that Galileo could see only as a tiny point of light through his primitive telescope. From the first fleeting glimpses provided by the Pioneer spacecraft to the detailed reconnaissance conducted by the Galileo orbiter, each mission has added new chapters to our understanding of this enigmatic moon. The Pioneer program represented humanity's first tentative steps into the outer solar system, a reconnaissance mission designed to prove that spacecraft could survive the journey to Jupiter and return useful scientific data. Pioneer 10, launched on March 2, 1972, became the first spacecraft to traverse the asteroid belt and the first to make close observations of Jupiter, reaching the giant planet in December of 1973. Pioneer 11 followed a year later, launching on April 5, 1973, and arriving at Jupiter in December of 1974, before continuing on to become the first spacecraft to visit Saturn. The Pioneer spacecraft were relatively simple by later standards, each weighing only about 260 kilograms and carrying a modest suite of instruments, including imaging photopolarimeters, magnetometers, plasma analyzers, and charged particle detectors. Their imaging systems were not true cameras, but rather instruments that built up pictures by scanning across targets as the spacecraft rotated, a technique that produced images of limited resolution compared to later missions. Nevertheless, the Pioneers provided humanity's first close-up views of Jupiter and its moons, including Callisto. Pioneer 10 passed within approximately 130,000 kilometers of Jupiter's cloud tops, far too distant from Callisto to obtain detailed images of the moon's surface. The images returned showed Callisto as a small fuzzy disk with hints of surface markings, but no clear details. Pioneer 11, following a trajectory that brought it closer to some of the Galilean moons, obtained slightly better views, but still could not resolve individual surface features. The primary contribution of the Pioneer missions to Callisto science was not in imaging, but in demonstrating that spacecraft could operate in the intense radiation environment near Jupiter, paving the way for more ambitious missions to follow. The Voyager program represented a quantum leap in outer solar system exploration, taking advantage of a rare alignment of the giant planets that occurs only once every 175 years to send two spacecraft on a grand tour of Jupiter, Saturn, Uranus, and Neptune. Voyager 1 and Voyager 2, launched in August and September of 1977, carried sophisticated instrument packages, including high-resolution cameras, infrared and ultraviolet spectrometers, magnetometers, and plasma science instruments, enabling detailed studies of every world they encountered. Voyager 1 reached Jupiter in March of 1979, passing within 350,000 kilometers of the planet and obtaining spectacular images of the Galilean moons. The spacecraft's closest approach to Callisto brought it within 126,000 kilometers of the moon's surface, close enough for the cameras to reveal surface details never before seen. The images returned by Voyager 1 showed a world saturated with impact craters, a surface so heavily bombarded that it appeared almost uniform in its cratered texture. The great multi-ring basins of Valhalla and Asgard were clearly visible, their concentric ring structures providing dramatic evidence of ancient catastrophic impacts. Voyager 2 arrived at Jupiter in July of 1979, following a trajectory that brought it within 214,000 kilometers of Callisto. While this was not as close as Voyager 1's approach, Voyager 2's images complemented those of its predecessor, providing coverage of different regions of the moon and different lighting conditions. Together, the two Voyager spacecraft mapped much of Callisto's surface a resolution sufficient to identify major geological features and characterize the overall nature of the terrain. The Voyager images revealed several surprising aspects of Callisto's geology. The extreme crater density confirmed that the surface was ancient, essentially unchanged since the period of heavy bombardment that marked the early solar system. The subdued, relaxed appearance of many craters indicated that viscous flow of ice had softened their features over time, providing information about the thermal history of the Moon. The dark, dirty appearance of the surface ice suggested extensive contamination by rocky materials and radiation-processed compounds, and the absence of any evidence for geological activity, no volcanic features, no tectonic structures, no signs of surface renewal, marked Callisto as fundamentally different from its more active siblings. Following the Voyager encounters, more than 15 years would pass before another spacecraft visited the Jovian system. The Galileo mission, named in honor of the astronomer who discovered Jupiter's moons, was designed for a comprehensive study of Jupiter and its satellites, spending years in orbit rather than making brief flybys. Launched on October 18th, 1989, Galileo followed a circuitous route to Jupiter, using gravity assists from Venus and Earth to gain enough energy to reach the outer solar system, finally arriving at Jupiter on December 7th, 1995. The Galileo spacecraft consisted of two main components: an orbiter that would circle Jupiter for years, making repeated flybys of the Galilean moons, and an atmospheric probe that would plunge into Jupiter's atmosphere to make direct measurements of its composition and structure. The orbiter carried a sophisticated instrument package, including a solid-state imaging camera, a near-infrared mapping spectrometer, an ultraviolet spectrometer, a photopolarimeter radiometer, a magnetometer, a plasma science instrument, an energetic particle detector, a plasma wave spectrometer, and a dust detector. This comprehensive suite of instruments enabled detailed studies of every aspect of the Jovian system. Galileo's primary mission lasted until December of 1997, but the spacecraft proved so capable and the scientific returns so valuable that the mission was extended multiple times, eventually continuing until September of 2003, when the spacecraft was deliberately plunged into Jupiter's atmosphere to prevent any possibility of contaminating Europa's potentially habitable ocean. During its 8 years of operations at Jupiter, Galileo completed 34 orbits of the giant planet, making numerous close flybys of all 4 Galilean moons. Callisto received particular attention from the Galileo mission, with the spacecraft making 8 close flybys of the Moon between November 1996 and May 2001. The closest of these encounters brought Galileo within just 138 kilometers of Callisto's surface, enabling imaging at resolutions as fine as 15 meters per pixel, revealing details completely invisible to the Voyager cameras. These close flybys also allowed precise measurements of Callisto's gravitational field and magnetic environment, providing crucial data about the Moon's interior structure. The high-resolution images returned by Galileo transformed our understanding of Callisto's surface geology. At the finest scales, the surface proved to be remarkably complex, with small craters, knobs, and other features creating a rough, irregular texture, quite different from the smooth appearance suggested by lower-resolution images. Bright patches of relatively clean ice were visible on some crater walls and peaks, suggesting that darker surface materials had slumped downward to expose fresher ice beneath. Strange landforms called pinnacles or spires, tall narrow features tens of meters high, dotted some regions, their origin still not fully understood. The Galileo magnetometer measurements during Callisto flybys provided the evidence for a subsurface ocean discussed earlier, one of the mission's most significant discoveries. By carefully analysing the variations in the magnetic field near Callisto, scientists determined that the Moon must contain a layer of electrically conducting material, most plausibly interpreted as a salty liquid water ocean beneath the ice shell. This finding elevated Callisto from a geologically dead world of purely historical interest to a potentially habitable environment worthy of future exploration. Following Galileo's demise in 2003, no dedicated mission to the Jovian system was launched for many years, though the New Horizons spacecraft made a brief flyby of Jupiter in February 2007 on its way to Pluto, obtaining some distant observations of the Galilean moons. The Juno spacecraft, which entered orbit around Jupiter in July 2016, was designed primarily to study Jupiter itself rather than its moons, but has obtained some observations of Callisto and the other Galilean satellites during its extended mission. The next major mission to explore the Jovian system is the European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, which launched on April 14, 2023, and is expected to arrive at Jupiter in 2031. JUICE will conduct detailed studies of Ganymede, Europa, and Callisto, including multiple flybys of Callisto that will provide new data on the Moon's surface, interior, and potential ocean. The spacecraft carries a comprehensive instrument suite, including cameras, spectrometers, a radar sounder capable of probing beneath the ice surface, and instruments to study the magnetic and plasma environment. NASA's Europa Clipper mission, launched in October 2024, is focused primarily on Europa, but will also make observations of the other Galilean moons during its orbital tour of the Jovian system. The spacecraft's powerful instrument suite, designed to characterize Europa's ice shell and ocean, will provide valuable data on Callisto during any close approaches, complementing the observations made by JUICE. These upcoming missions promise to revolutionize our understanding of Callisto, answering questions that have lingered since the Voyager and Galileo eras, and undoubtedly raising new questions that will inspire future generations of exploration. The story of Callisto's exploration is far from complete. In many ways, it is just beginning. Chapter 11. Callisto as a future human destination, gateway to the outer solar system. Among all the moons of the outer solar system, Callisto holds a special place in the dreams of those who envision a future where humans live and work beyond the confines of Earth. While Mars has captured most of the public imagination as the next destination for human explorers, and while Europa's potential for life makes it a compelling scientific target, Callisto offers unique advantages that have led NASA and other space agencies to seriously consider it as a site for future human operations in the Jovian system. The primary advantage of Callisto as a human destination is its relatively benign radiation environment. Jupiter possesses the most intense radiation belts of any planet in the solar system. Belts of energetic charged particles trapped by the planet's powerful magnetic field that would deliver lethal doses of radiation to unprotected humans within hours or days. These radiation belts extend outward from Jupiter, encompassing the orbits of Io, Europa, and Ganymede, making extended human presence on these moons extremely challenging without massive shielding. Callisto, however, orbits beyond the most intense regions of Jupiter's radiation belts. At its distance of nearly 1.9 million kilometers from Jupiter, Callisto receives radiation doses roughly 300 times lower than those at Europa's orbit. low enough that humans could potentially live and work on Callisto's surface with reasonable shielding measures. This radiation advantage makes Callisto the only Galilean moon where long-term human habitation might be feasible with near-term technology. A human outpost on Callisto could serve multiple purposes. Most immediately, it could function as a base for scientific exploration of the Jovian system, supporting robotic missions to Europa, Ganymede, and Io, while providing a safe haven for human researchers. The ability to have humans in the loop, making real-time decisions and conducting hands-on science, could dramatically accelerate the pace of discovery compared to purely robotic exploration controlled from Earth with its 45 to 52-minute one-way communication delay. Beyond supporting Jovian system science, a Callisto base could serve as a stepping stone for human exploration of the outer solar system. Located at the edge of Jupiter's gravitational influence, Callisto could function as a way station for missions to Saturn, Uranus, Neptune, and beyond. Spacecraft could refuel at Callisto using resources extracted from the moon's abundant water ice, reducing the amount of propellant that must be carried from Earth and making ambitious outer solar system missions more feasible. The resources available on Callisto would be crucial for any sustained human presence. Water ice, the dominant component of the surface, could be extracted and processed to provide drinking water, oxygen for breathing, and hydrogen and oxygen for rocket fuel. The rocky component of the surface might contain useful minerals, though the exact composition and accessibility of these materials remains uncertain. Solar power would be limited at Callisto's distance from the Sun, but nuclear power systems could provide reliable energy for habitats and industrial processes. Living conditions on Callisto would be challenging, but not impossible. The surface temperature averages around -139 degrees Celsius, requiring well-insulated habitats and protective suits for any surface activities. The low gravity, about 1/8 of Earth's, would require adaptation by human inhabitants and might have long-term health effects that are not yet fully understood. The lack of a significant atmosphere means that habitats would need to be pressurized and that meteorite impacts, even small ones, could pose hazards to surface structures. Several conceptual studies have examined what a human mission to Callisto might look like. A 2003 NASA study called Revolutionary Concepts for Human Outer Planet Exploration, or HOPE, examined the feasibility of human missions to Callisto and other outer solar system destinations. The study concluded that a human mission to Callisto could potentially be accomplished within several decades using advanced propulsion technologies such as nuclear thermal or nuclear electric systems, which would dramatically reduce transit times compared to conventional chemical rockets. The HOPE study envisioned a mission architecture in which a crew would travel from Earth to Callisto over a period of 2 to 5 years. Depending on the propulsion system used, establish a surface base, conduct scientific operations for an extended period, and then return to Earth. The study identified numerous technical challenges that would need to be overcome, including developing reliable life support systems for multi-year missions, protecting crews from radiation during the transit through interplanetary space, and creating surface systems capable of operating in Callisto's harsh environment. More recent studies have continued to refine concepts for human operations at Callisto. Some envision permanent or semi-permanent bases that would be continuously occupied, supported by regular resupply missions from Earth or from other locations in the solar system. Others propose intermittent human presence, with crews visiting for limited periods to conduct specific scientific campaigns before returning to Earth or to bases elsewhere. The optimal approach would depend on many factors, including the pace of technological development, the scientific priorities of the space agencies involved, and the broader context of human expansion into the solar system. The timeline for human missions to Callisto remains highly uncertain. Current human spaceflight programs are focused on returning to the Moon and eventually sending humans to Mars, goals that will likely occupy the next several decades. A human mission to Callisto would require capabilities significantly beyond those needed for Mars, including more powerful propulsion systems, more capable life support, and more autonomous operations given the communication delays involved. Optimistic projections suggest that human missions to the outer solar system might become feasible in the second half of the 21st century, but much depends on the pace of technological progress and the priorities of future generations. Regardless of when humans eventually reach Callisto, the Moon's potential as a base for outer solar system exploration ensures that it will remain a subject of serious study and planning. The vision of humans standing on Callisto's ancient surface, gazing up at the giant banded disk of Jupiter hanging in the black sky, represents one of the most compelling possibilities for our species' future among the stars. Chapter 12. Callisto's role in understanding planetary formation, a window into the early solar system. Beyond its potential as a destination for exploration and its status as a possible ocean world, Callisto serves a crucial role in planetary science as a natural laboratory for understanding how worlds form and evolve. The Moon's ancient surface, its partially differentiated interior, and its position at the outer edge of the Jovian system all provide unique insights into processes that shaped the solar system during its earliest epochs. The formation of the Galilean moons is thought to have occurred within a disk of gas and dust that surrounded the young Jupiter, analogous to the protoplanetary disk from which the planets themselves formed around the young Sun. This circumjovian disk, fed by material falling inward from the broader solar nebula, provided the raw materials from which Io, Europa, Ganymede, and Callisto accreted over a period of perhaps a few 100,000 to a few million years. The properties of each moon reflect the conditions in the part of the disk where it formed. Callisto's great distance from Jupiter meant that it formed in a region of the circumjovian disk that was relatively cold, where water ice could exist as a solid and become incorporated into the growing moon. The closer moons formed in warmer regions where ice was less abundant, which partly explains the gradient in density observed among the Galilean satellites, with rocky, dense Io closest to Jupiter and icy, low-density Callisto farthest away. This density gradient mirrors the pattern seen in the solar system as a whole, with dense, rocky planets close to the Sun and icy bodies predominating in the outer reaches. The partial differentiation of Callisto's interior presents a puzzle that has implications for understanding moon formation more broadly. As discussed earlier, most large moons and planets have fully differentiated, with dense materials sinking to form cores and light materials rising to form crusts. Callisto's incomplete differentiation suggests either that the moon never got hot enough to allow full separation of materials, or that some process arrested the differentiation before it could be completed. One influential hypothesis proposes that Callisto formed relatively slowly over a period of perhaps 1,000,000 years or more, allowing heat to escape as fast as it was generated by impacts and preventing the interior from ever becoming hot enough for complete melting. Ganymede, by contrast, may have formed more rapidly, accumulating so much heat during its formation that it fully melted and differentiated. This difference in formation timescale could explain why two moons of similar size and composition ended up with such different internal structures. Testing this hypothesis requires detailed knowledge of the Moon's internal structures, knowledge that can only be obtained through sophisticated measurements by future spacecraft. The JUICE mission, with its radar sounder and gravity science instruments, will provide new constraints on the interior structures of both Ganymede and Callisto, potentially resolving the question of why these sibling moons evolve so differently. Callisto's ancient surface provides another window into the early solar system, preserving a record of the impact flux during the period of heavy bombardment that ended roughly 3.8 billion years ago. By counting craters of different sizes and estimating their ages, scientists can reconstruct the history of bombardment in the outer solar system and compare it to the record preserved on the Moon and other inner solar system bodies. Such comparisons provide information about the sources of impactors, the dynamics of the early solar system, and the processes that delivered water and organic materials to the planets. The crater record on Callisto suggests that the impact flux in the outer solar system may have been different from that in the inner solar system, with a different size distribution of impactors or a different time history of bombardment. Understanding these differences requires careful analysis of crater populations on multiple outer solar system bodies, a task that will be advanced by the high-resolution imaging expected from JUICE and other future missions. Callisto also provides insights into the behavior of ice rock mixtures under planetary conditions, a topic relevant to understanding not only the Galilean moons, but also the many other icy bodies in the outer solar system, including the moons of Saturn, Uranus and Neptune, the dwarf planets of the Kuiper Belt, and the countless small icy bodies that populate the outer reaches of our cosmic neighbourhood. The viscous relaxation of Callisto's craters, the possible presence of a subsurface ocean, and the thermal evolution of the interior all depend on the physical properties of ice rock mixtures at low temperatures and high pressures, properties that are still being studied in laboratories on Earth. The questions raised by Callisto extend beyond our own solar system to the countless planetary systems orbiting other stars. If moons like Callisto can form around giant planets and maintain subsurface oceans for billions of years, then similar worlds may be common throughout the galaxy. The study of Callisto thus contributes to our understanding of planetary habitability in the broadest sense, informing the search for life beyond Earth and the assessment of how common Earth-like conditions might be in the universe. Chapter 13. Mysteries Remaining. Questions for Future Generations. Despite decades of study by Earth-based telescopes and visiting spacecraft, Callisto retains many mysteries that await resolution by future observations and missions. These unanswered questions span topics from the Moon's deep interior to its tenuous atmosphere, from its ancient past to its potential for harbouring life. The nature of Callisto's interior remains one of the most fundamental uncertainties. While the evidence for a subsurface ocean is compelling, the depth, thickness, and composition of this ocean are poorly constrained. Is the ocean a thin layer sandwiched between ice shells, or a vast reservoir hundreds of kilometres deep? Is it in contact with rocky material that might provide chemical nutrients for life, or isolated within an icy matrix? What is the salt content of the ocean, and what other dissolved substances might it contain? Answering these questions will require measurements that can probe beneath Callisto's surface, such as the radar soundings planned for the JUICE mission or seismic measurements from future landers. The degree and nature of Callisto's internal differentiation also remains uncertain. The current models, based primarily on gravity measurements from Galileo, suggest partial differentiation, but the details of the internal structure are not well constrained. Does Callisto possess a small rocky core, or is rock distributed throughout the interior? How does the ice-rock ratio vary with depth? What is the thermal structure of the interior, and how has it evolved over time? More precise gravity measurements, combined with other geophysical data, will be needed to answer these questions. The origin of Callisto's surface features presents numerous puzzles. The multi-ring basins of Valhalla and Asgard are reasonably well understood as the products of large impacts into an icy crust, but many smaller-scale features remain enigmatic. The bright patches on crater walls and peaks may represent exposed clean ice, but the processes that expose this ice are not fully understood. The strange pinnacles or spires observed in some high-resolution Galileo images have no clear analogue on other bodies and may represent a unique form of ice erosion or deposition. The dark material that covers much of the surface has not been definitively identified, and its origin, whether from external sources like meteoritic infall or from internal processes, remains debated. The thin atmosphere of Callisto raises its own set of questions. The carbon dioxide exosphere detected by Galileo is understood in broad terms as the product of sublimation from surface ice, but the detailed processes that maintain this atmosphere against continuous loss to space are not fully characterized. The molecular oxygen component, produced by radiolysis of water ice, varies in ways that are not completely explained by current models. Future missions with more sensitive atmospheric instruments may reveal additional trace species and provide better constraints on the sources and sinks of atmospheric gases. Perhaps the most profound question concerns the potential for life within Callisto's subsurface ocean. If such an ocean exists, and if it has persisted for billions of years, could it harbour living organisms? The conditions within Callisto's ocean would be very different from those on Earth's surface. Dark, cold, and possibly isolated from the chemical energy sources that power most terrestrial ecosystems. Yet life on Earth has proven remarkably adaptable, thriving in environments once thought too extreme for any organism. The question of whether life could arise and persist in Callisto's hidden ocean remains open, awaiting future missions that can probe beneath the ice and sample the waters below. These mysteries ensure that Callisto will remain a subject of scientific fascination for generations to come. Each question answered will undoubtedly raise new questions, as is the nature of scientific inquiry. The ancient cratered moon that Galileo first glimpsed as a tiny point of light more than 4 centuries ago continues to challenge and inspire us. A reminder of how much remains to be discovered in our cosmic neighbourhood. Chapter 14. The broader context. Callisto among the ocean worlds. As we contemplate Callisto's place in the grand scheme of planetary science, it becomes clear that this moon is part of a larger story, the story of ocean worlds scattered throughout our solar system and perhaps throughout the galaxy. The discovery that liquid water can persist beneath the icy surfaces of moons, far from the warmth of the sun, has revolutionized our understanding of where life might exist and has expanded the horizons of astrobiology in ways that would have seemed like science fiction just a few decades ago. The concept of ocean worlds emerged gradually as spacecraft explored the outer solar system and revealed the surprising diversity of icy moons. Europa was the first to capture scientific attention as a potential abode for life, its young fractured surface suggesting active geology and a possible liquid water layer beneath. The Galileo mission's discovery of induced magnetic fields at Europa, Ganymede, and Callisto provided strong evidence that subsurface oceans are common among the large icy moons of Jupiter. Meanwhile, the Cassini mission to Saturn revealed that tiny Enceladus, only about 500 kilometers in diameter, possesses a global subsurface ocean that vents into space through dramatic geysers at the Moon's south pole. These discoveries have transformed the search for extraterrestrial life. The traditional concept of the habitable zone, the region around a star where surface temperatures allow liquid water to exist, now seems too narrow. Moons like Europa, Enceladus, and potentially Callisto demonstrate that liquid water can be maintained by internal heat sources, primarily tidal heating, far beyond the conventional habitable zone. This realization has profound implications for the prevalence of habitable environments in the universe, suggesting that ocean worlds may be far more common than Earth-like planets with surface oceans. Callisto occupies a unique position among the known ocean worlds. Unlike Europa and Enceladus, which show clear signs of ongoing geological activity driven by tidal heating, Callisto appears geologically quiescent, its ancient surface unchanged for billions of years. If Callisto does possess a subsurface ocean, it must be maintained by a different mechanism than the tidal heating that warms its more active siblings. The most likely candidate is the slow decay of radioactive elements within Callisto's rocky component, a heat source that operates in all rocky and icy bodies, but is usually insufficient to maintain liquid water without additional contributions from tidal or other heating mechanisms. The persistence of an ocean within Callisto, if confirmed, would demonstrate that even minimal internal heating can maintain liquid water over geological timescales under the right conditions. This finding would have significant implications for the prevalence of ocean worlds throughout the solar system and beyond. Many icy bodies in the outer solar system, including dwarf planets like Pluto and Eris, moons of Uranus and Neptune, and countless smaller objects in the Kuiper belt, might harbour subsurface oceans maintained by radioactive heating alone. The universe might be filled with hidden oceans, dark and cold, but potentially habitable, waiting to be discovered. The comparison between Callisto and other ocean worlds also highlights the diversity of conditions that might exist within subsurface oceans. Europa's ocean is thought to be in direct contact with a rocky seafloor, where hydrothermal vents might provide the chemical energy and nutrients necessary to support life. Enceladus's ocean shows evidence of active hydrothermal processes, with hydrogen gas detected in its plumes, suggesting water-rock reactions at elevated temperatures. Callisto's ocean, by contrast, may be sandwiched between layers of ice, isolated from rocky material and potentially lacking the chemical energy sources that might support life. This diversity of ocean world environments presents both challenges and opportunities for astrobiology. On one hand, it suggests that not all subsurface oceans are equally promising as potential habitats for life. An ocean isolated within ice, lacking energy sources and nutrients, might be sterile despite the presence of liquid water. On the other hand, the diversity of ocean worlds provides multiple natural laboratories for studying the conditions necessary for life, allowing scientists to compare environments and identify the factors that distinguish habitable from uninhabitable oceans. Future exploration of ocean worlds will require new technologies and approaches. Penetrating the ice shells of moons like Europa and Callisto to sample the oceans below presents enormous engineering challenges. The ice shells may be tens to hundreds of kilometers thick, far beyond the reach of conventional drilling technology. Proposed approaches include ice-penetrating probes that melt their way through the ice, autonomous submarines that could explore the oceans once reached, and instruments that can detect signs of life in material ejected from the oceans through cracks or plumes. For Callisto specifically, the lack of obvious surface activity makes accessing the subsurface ocean particularly challenging. Unlike Enceladus, which conveniently vents ocean material into space where it can be sampled by passing spacecraft, Callisto shows no signs of plumes or other surface expressions of its hidden ocean. Any mission to sample Callisto's ocean would need to penetrate the ice shell directly, a formidable undertaking that lies beyond current technological capabilities, but may become feasible as space exploration technology advances. Chapter 15: Callisto in Human Culture and Imagination. Beyond its scientific significance, Callisto has captured the human imagination in ways that reflect our eternal fascination with distant worlds and the possibilities they represent. From the mythological origins of its name to its appearances in science fiction and its role in visions of humanity's future among the stars, Callisto has become part of our cultural landscape, a symbol of the mysteries that await us in the outer reaches of the solar system. The mythological Callisto, the beautiful huntress transformed into a bear and placed among the stars, represents themes of transformation, exile, and eternal wandering that resonate across cultures and centuries. The story speaks to the human experience of change and loss, of being cast out from familiar surroundings into strange new circumstances. In naming the outermost Galilean moon after this tragic figure, Simon Marius, perhaps unknowingly, created a fitting metaphor for a world that exists in cosmic isolation, far from the warmth of the sun, bearing the scars of ancient violence on its frozen surface. Science fiction writers have long been drawn to the moons of Jupiter as settings for their stories, and Callisto has featured in numerous works of imaginative literature. In some stories, Callisto serves as a frontier outpost, a remote base for explorers and scientists studying the Jovian system. In others, it becomes a refuge for those fleeing the crowded inner solar system, a place where hardy colonists carve out new lives on an alien world. The moon's ancient, cratered surface and its position at the edge of Jupiter's domain make it a natural setting for tales of isolation, discovery, and survival. Arthur C. Clarke, one of the giants of science fiction, featured Callisto in his novel 2061 Odyssey 3, part of his famous Space Odyssey series. In Clarke's vision, Callisto serves as a base for human operations in the Jovian system, a role that reflects the moon's real advantages as a relatively safe haven from Jupiter's intense radiation. Other authors have imagined Callisto as the site of alien artifacts, hidden bases, or mysterious phenomena, using the moon's remoteness and ancient surface as a canvas for stories of wonder and discovery. The visual arts have also embraced Callisto, with space artists creating stunning depictions of the moon's cratered landscape, the looming presence of Jupiter in its sky, and the stark beauty of its icy terrain. These artistic visions, informed by scientific data but enhanced by imagination, help bring Callisto to life for audiences who may never see the actual spacecraft images. They remind us that exploration is not just a scientific endeavour but also an aesthetic and emotional one, driven by our desire to see and understand the beauty of the cosmos. In the realm of video games and interactive media, Callisto has appeared as a setting for adventures ranging from realistic simulations of space exploration to fantastical tales of alien encounters. The 2022 video game The Callisto Protocol used the moon as the setting for a survival horror experience, imagining a prison facility on Callisto where terrible events unfold. While such fictional depictions take considerable liberties with scientific accuracy, they demonstrate the hold that Callisto and other outer solar system destinations have on popular imagination. The cultural significance of Callisto extends beyond entertainment to encompass broader questions about humanity's place in the universe and our future as a spacefaring species. When scientists and engineers discuss the possibility of human missions to Callisto, they are not just planning technical operations, but also imagining a future in which humans have expanded beyond Earth to become a truly interplanetary civilization. Callisto, with its potential as a base for outer solar system exploration, represents a stepping stone on this grand journey, a waypoint on the path to the stars. The naming of features on Callisto's surface reflects this cultural dimension of planetary exploration. The International Astronomical Union, which oversees the naming of celestial bodies and their features, has assigned names from Norse mythology to the major features on Callisto, creating a thematic connection to the ancient stories of gods and heroes. Valhalla, the great hall where slain warriors feast with Odin, lends its name to the largest impact basin. Asgard, the realm of the gods, names the second largest basin. Smaller features bear names like Heimdall, the watchman of the gods, and Skuld, one of the Norns who weave the fates of gods and men. This naming convention creates a poetic resonance between the ancient myths and the modern science, linking our exploration of distant worlds to the stories our ancestors told around their fires. The warriors of Valhalla, feasting eternally in their great hall, find an echo in the frozen plains of an impact basin on a moon of Jupiter, a connection across time and space that speaks to the continuity of human curiosity and imagination. Chapter 16. Reflections on Deep Time, Callisto as a Cosmic Archive. As we near the end of our journey through the story of Callisto, it is worth pausing to reflect on what this ancient moon teaches us about time, change, and the nature of the cosmos. Callisto's surface, essentially unchanged for 4 billion years, serves as a kind of cosmic archive, preserving a record of events that occurred when the solar system was young and the processes that would shape the planets were still unfolding. 4 billion years is a span of time almost impossible for the human mind to grasp. When the craters that cover Callisto's surface were forming, Earth was a very different world, still cooling from its violent formation, bombarded by the same rain of debris that scarred Callisto and the other bodies of the solar system. Life on Earth, if it existed at all, consisted of nothing more than simple, single-celled organisms, the ancestors of all the complex life that would eventually evolve. The continents we know today did not exist. The atmosphere was unbreathable. The oceans were young and perhaps still forming. In the time since Callisto's surface was shaped by that ancient bombardment, Earth has been transformed beyond recognition. Continents have drifted across the globe, colliding and separating in a slow dance of plate tectonics. Life has evolved from simple cells to the incredible diversity of organisms that populate our planet today, including a species capable of building telescopes and spacecraft to study distant moons. Entire mountain ranges have risen and eroded away. Oceans have opened and closed. Ice ages have come and gone. The history of Earth is a story of constant change, of transformation and renewal. Callisto, by contrast, has remained essentially static. The craters that formed 4 billion years ago are still there, softened by the slow flow of ice but otherwise unchanged. No volcanoes have erupted to bury them under fresh lava. No tectonic forces have cracked and shifted the crust. No oceans have risen to erode their rims. Callisto is a world where time seems to have stopped, a frozen snapshot of the early solar system preserved in ice and rock. This contrast between the dynamic Earth and the static Callisto highlights the importance of internal heat in driving planetary evolution. Earth remains geologically active because its interior is still hot, warmed by the decay of radioactive elements and by the residual heat of formation. This internal heat drives plate tectonics, powers volcanoes, and maintains the magnetic field that protects our atmosphere from the solar wind. Without this heat, Earth would eventually become as geologically dead as Callisto, its surface frozen and unchanging. Callisto's quiescence also reflects its position in the Jovian system, far from the tidal forces that keep Io volcanically active, and that may drive geological activity on Europa and Ganymede. The same isolation that protects Callisto from Jupiter's intense radiation also deprives it of the tidal heating that might otherwise warm its interior and drive surface renewal. Callisto is a world that has been left alone, undisturbed by the forces that shape its more active siblings. The preservation of Callisto's ancient surface makes it an invaluable scientific resource, a window into the early history of the solar system that has been closed on most other worlds. By studying the craters on Callisto, scientists can learn about the population of impactors that existed 4 billion years ago, the rate at which impacts occurred, and the processes that shape the surfaces of icy bodies in the outer solar system. This information helps us understand not just Callisto, but the entire solar system, providing context for the geological histories of other worlds. Yet Callisto's ancient surface also evokes a sense of melancholy, a reminder of the vast stretches of time during which nothing much happens, the long silences between the dramatic events that punctuate cosmic history. For 4 billion years, Callisto has circled Jupiter in its stately orbit, its surface slowly accumulating the scars of occasional impacts, but otherwise unchanging. The universe is full of such quiet places, worlds, where time passes without incident, where the drama of life and change that characterizes Earth is absent. This perspective can be humbling, reminding us of how special and precious our own dynamic, living world truly is. Earth is not just another rock in space, but a rare and wonderful place where the conditions have aligned to allow the emergence of life and consciousness. The contrast with Callisto, beautiful in its own stark way, but lifeless and unchanging, underscores the value of what we have and the importance of protecting it. Chapter 17. Looking Forward. The Future of Callisto Exploration. As we look to the future, the exploration of Callisto stands poised to enter a new era. The missions currently en route to the Jovian system, JUICE and Europa Clipper, will provide unprecedented data on Callisto and its siblings, answering some of the questions that have lingered since the Voyager and Galileo eras, while undoubtedly raising new ones. Beyond these missions, scientists and engineers are already dreaming of more ambitious endeavours that could transform our understanding of this ancient moon. The JUICE mission, developed by the European Space Agency, represents the most comprehensive exploration of the Jovian system since Galileo. Launched in April 2023, JUICE is scheduled to arrive at Jupiter in 2031 after a complex trajectory involving gravity assists from Earth and Venus. Once in the Jovian system, the spacecraft will conduct multiple flybys of Europa, Ganymede and Callisto before eventually entering orbit around Ganymede, becoming the first spacecraft to orbit a moon other than Earth's own. For Callisto, JUICE will conduct at least 12 close flybys, approaching to within 200 kilometers of the surface. The spacecraft's instrument suite includes cameras capable of imaging the surface at resolutions better than those achieved by Galileo, spectrometers that can map the composition of surface materials in detail, a radar sounder that can probe beneath the surface to detect subsurface structures, including a possible ocean, and instruments to characterize the magnetic and plasma environment. These observations will provide new insights into Callisto's geology, composition, interior structure, and potential habitability. The radar sounder, called RIME for Radar for Icy Moons Exploration, is particularly exciting for Callisto science. This instrument will send radio waves into the subsurface and detect reflections from boundaries between materials of different properties, such as the interface between ice and liquid water. If Callisto possesses a subsurface ocean, RIME may be able to detect it directly, providing confirmation of what is currently inferred from magnetic field measurements. The radar will also reveal the structure of the ice shell, including any layers or heterogeneities that might provide clues to Callisto's geological history. NASA's Europa Clipper mission, launched in October 2024, is focused primarily on Europa, but will also contribute to Callisto science. The spacecraft's trajectory through the Jovian system will bring it close to Callisto on several occasions, and its powerful instrument suite, designed to characterize Europa's ice shell and ocean, will provide valuable data on Callisto as well. The synergy between JUICE and Europa Clipper, with two sophisticated spacecraft exploring the Jovian system simultaneously, promises a golden age of discovery for all the Galilean moons. Beyond these approved missions, scientists have proposed various concepts for more ambitious Callisto exploration. Lander missions could place instruments directly on Callisto's surface, conducting detailed studies of surface composition, seismic activity, and other properties that cannot be measured from orbit. Such missions would face significant challenges, including the need to survive Callisto's extreme cold and to communicate across the vast distance to Earth, but they are technically feasible with current or near-term technology. More ambitious still are concepts for subsurface exploration, missions that would penetrate Callisto's ice shell to search for and potentially sample the ocean below. Such missions remain in the realm of advanced concepts, requiring technologies that do not yet exist, but they represent the ultimate goal of ocean world exploration. The ability to directly sample the waters of Callisto's ocean to search for signs of life in that hidden realm would be one of the greatest achievements in the history of exploration. The timeline for such ambitious missions remains uncertain, dependent on technological progress, funding priorities, and the results of nearer-term exploration. The JUICE and Europa Clipper missions will provide crucial information that will shape future exploration strategies, potentially revealing whether Callisto's ocean is a promising target for life detection or a sterile reservoir of little astrobiological interest. The answers to these questions will determine whether Callisto becomes a high-priority target for future exploration or takes a back seat to more promising destinations. Regardless of what future exploration reveals, Callisto will remain an important part of our understanding of the solar system and our vision of humanity's future in space. Whether as a scientific target, a potential habitat for life, or a stepping stone for human expansion into the outer solar system, Callisto has secured its place in the story of exploration. Chapter 18. A closing meditation. Callisto in the cosmic perspective. As we bring our journey through the story of Callisto to a close, let us take a moment to step back and consider this distant moon in the broadest possible context, as one small world among the countless worlds that populate our universe. In doing so, we gain not just scientific knowledge, but also a sense of perspective, a feeling for our place in the grand scheme of things that is one of the greatest gifts of astronomical exploration. Callisto orbits Jupiter at a distance of nearly 1.9 million kilometers, a vast gulf of empty space that would take a beam of light more than 6 seconds to cross. Jupiter itself orbits the Sun at an average distance of about 778 million kilometers, more than 5 times the distance from Earth to the Sun. At this remote location, sunlight is weak, temperatures are frigid, and the familiar warmth of our home star is reduced to a bright but distant point in the sky. Yet even Jupiter's orbit is a mere stone's throw in cosmic terms. The nearest star, beyond the Sun, Proxima Centauri, lies at a distance of about 4.2 light-years, or roughly 40 trillion kilometres. The Milky Way galaxy, our cosmic home, spans about 100,000 light-years and contains hundreds of billions of stars, many of which likely possess their own planetary systems with their own moons. The observable universe contains hundreds of billions of galaxies, each with its own hundreds of billions of stars, stretching across a volume of space so vast that light from the most distant objects has been travelling for more than 13 billion years to reach us. In this cosmic context, Callisto is almost inconceivably small and insignificant, a tiny ball of ice and rock orbiting one planet around one star in one galaxy among billions. Yet this perspective, far from diminishing Callisto's importance, actually enhances it. For Callisto is one of the few worlds in this vast universe that we have actually visited, one of the handful of places beyond Earth where human-built machines have travelled and returned images and data. In a universe of unimaginable scale, Callisto is part of our neighbourhood, a place we can study and understand and perhaps one day visit in person. The exploration of Callisto and other worlds in our solar system represents humanity's first tentative steps into the cosmos, the beginning of a journey that may eventually take us to the stars. Each mission we send, each discovery we make, adds to our understanding of the universe and our place within it. The knowledge we gain is not just scientific data, but also wisdom, a deeper appreciation of the beauty and complexity of the cosmos and of the preciousness of our own living world. Callisto, with its ancient cratered surface and its hidden ocean, embodies both the mystery and the promise of space exploration. Mystery, because so much remains unknown about this distant moon, from the details of its interior structure to the question of whether life might exist in its subsurface waters. Promise, because each mystery is an invitation to explore, to send new missions, to develop new technologies, to push the boundaries of what is possible. The story of Callisto is not finished. It is still being written by the scientists who study it, by the engineers who build the spacecraft to explore it, and by all of us who look up at the night sky and wonder what lies beyond. As you drift towards sleep, carried by the gentle rhythm of these words, perhaps you can imagine yourself standing on Callisto's ancient surface, gazing up at the giant banded disk of Jupiter hanging in the black sky. The stars shine with a brilliance unknown on Earth, undimmed by atmosphere, countless points of light scattered across the velvet darkness. The silence is absolute, broken only by the whisper of your own breathing within your spacesuit. Beneath your feet, the ice stretches away to the horizon, cratered and ancient, unchanged for 4 billion years. In this moment of imagination, you're connected to something larger than yourself, to the grander story of cosmic evolution that has brought matter and energy together in ever more complex configurations, from the primordial hydrogen of the early universe to the stars that forged heavier elements in their nuclear furnaces, to the planets and moons that formed from the debris of stellar explosions, to the life that emerged on at least one world and developed the curiosity and capability to explore the others. You are part of this story, a conscious being contemplating the universe that gave rise to you, standing in imagination on a world that exists in reality, waiting to be explored. The story of Callisto is, in the end, a human story, a story of curiosity and courage, of the drive to understand and explore that has characterized our species, since our ancestors first looked up at the stars and wondered what they were. From Galileo's first glimpse of a tiny point of light near Jupiter to the sophisticated spacecraft that have revealed Callisto's cratered surface and hidden ocean, the exploration of this distant moon represents one thread in the great tapestry of human inquiry, a thread that connects us to our past and points toward our future. And so, as sleep approaches and the day's concerns fade into the background, carry with you the image of Callisto, that ancient cratered moon orbiting far from the sun, bearing the scars of 4 billion years of cosmic history, hiding an ocean in its depths, waiting patiently for the explorers who will one day unlock its secrets. In the vastness of space and time, Callisto endures, a testament to the beauty and mystery of the universe we are privileged to inhabit. Thank you so much for joining me on this journey through the story of Callisto. If you enjoyed this exploration of one of the solar system's most fascinating moons, please consider giving this video a like and subscribing to the channel for more journeys through the wonders of space. Your support helps make these deep dives into cosmic topics possible, and I am grateful for every one of you who takes the time to explore the universe with me. Until next time, sleep well, dream of distant worlds, and remember that the cosmos is always there, waiting to be discovered.